Thanks for having me. It's really cool. This is the first time I speak at New York City Ruby, and I'm happy to be a guinea pig for this remote experiment. Um, yeah, so I'm here to talk about the tar pit. First of all, how to avoid it in the first place, and then how to escape it if you're in it. Um, if you want to reach out to me on Twitter after this meetup, feel free to reach out via my handle is Tegwerker. So you can send me a message there, and I'm pretty quick to respond. Cool. So a few things about me. I am originally from Argentina. So if you hear any words that sound funny, it's because English is not my first language. And sometimes I just try to find the best word, and it is not the best word. Anyway, I have been living in Philadelphia for the past 3 years. I live here with my wife and daughter. So if you hear any crazy noises, it might be my daughter resisting, bedtime, dinner, and going to bed. So yeah, keep that in mind. And another thing about me is that I love open source. I wouldn't be here speaking at this meetup if it wasn't thanks to open source. Actually, about 99% of the code that I'm going to talk about today was not written by me, and maybe like 1% was an extension to existing libraries. So I do maintain a couple of gems you might have heard of. Database Cleaner is a library that helps you keep a clean database state between test runs. Bundler Leak is a library that helps you find dependencies that are known to have a memory leak in your gemfile.log. And NextRails is a toolkit that helps you upgrade your Rails application. It helps you find incompatibilities with the next version of Rails, and it helps you dual boot your application. When I'm not working on open source, I'm the founder of Ombu Labs, which is a small software development shop based in Philadelphia. We are about 9 people with, I guess 10 with a contractor. And we like to work a lot with Ruby, Rails, and JavaScript. And we also like to contribute as much as possible to the open source community. So you might have seen some of our work out there. Now, a few years ago, we found ourselves working a lot on Ruby on Rails upgrades. And what we did is we launched a service that was all about that. And we call that fastruby.io. This is a productized service. Companies hire us to ship their Rails upgrade projects. They know they need to upgrade, but they just don't want their teams to lose focus and work on it. So they outsource that kind of work to us. And yeah, some of the tools that I mentioned came out of the work that we do there. And a lot of the insights that I'm going to share with you come from our experience assessing technical debt in projects that we need to evaluate every month. Now, the inspiration for this talk is a book by one of my favorite authors, Fred Brooks. So Fred Brooks, many, many years ago, wrote the Mythical Man Month, and the very first chapter is all about the tar pit. And you might be familiar with this prehistorical scene of, giant beasts getting entangled in the tar. And, the more the struggle, the harder it is to get out. And he goes on to compare large system programming to this scene. It says, like, over the past decade, it's been such a tar pit. And many great and powerful beasts have thrashed violently in it. And what I love about this is that he's talking about the past decade being the 60s and the 70s. And to this day, there are issues that are mentioned in that chapter that are still with us today. So I love that. Like, some of his work is really interesting. And one of his essays you might have heard of, it's called No Silver Bullet. I highly recommend you read that after this meetup, if you haven't already. And then he goes on to say, yeah, the fiercer the struggle, the more entangling the tar, and no beast is so strong or so skillful, but that they ultimately sink. And in reality, it's if you haven't been in the tar pit, you might be in it in the future. And it looks like you are trying to make progress and you're trying to pay off technical debt, you're trying to ship features and you're trying to fix bugs and all that. But the more you try, the harder it gets. And I believe we're either in the tar pit and trying to get out of it, or we're trying to avoid the tar pit. We're trying to actively ship work that avoids the tar pit. And sometimes it looks like this when we're trying to get out. The Simpsons, of course, always have the best gifts. We make our best efforts and it just gets us deeper and deeper in the tar. Okay, so let's come back to reality, okay? Like, when do you see something like this? Well, the usual is like projects running over budget, estimating that a bunch of changes is going to take a month, and then 2 months in, you have no idea when you're going to be done. Taking forever to ship small changes. You inherited a project and you said, this small change is going to be done in a day, and a week goes by and you still have no idea when you're going to be done. And finally, the classic, sacrificing quality and increasing technical debt to be paid off later. But later never comes, and it just keeps getting worse and worse. And then the picture looks like this. Well, I'm here to tell you that it is not fine. You can slowly start putting off the fire in a measured way, of course. You don't want to start doing it in a way that is just like following your gut. You want to have like a measured way to start paying off technical debt. So this talk is split in 2 parts. The first one is, how do we avoid it in the first place? There are a bunch of tools that we can use. There are free and open source in our Ruby community that are great. And I'm going to explain how you can use them. And in the second part, you're going to use the same tools to gradually pay off technical debt. So part 2 kind of builds on top of part 1. All right, let's get started. Next week, boss might come along and tell you something like this. Yeah, if you could come in on this great legacy project and maintain it from now on, that would be great. For us at fastruby.io, it looks exactly the same, but instead of a boss, we have a client that is telling us that this is a great legacy Rails project. Now, before you commit to saying, yeah, I can ship this, I can work on this, you might want to think about what the next question is going to be, which is, how long is this tiny change going to take? And then the next words, of course, are going to be, because I need it by end of day today. So we need to find a way to not commit before we look at the source code, right? Like that's what I recommend to everybody. So how can we quickly assess code quality? Well, the good news is that we can assess quality with a bunch of tools. There are paid services like CodeClimate and CodeScene, and I bet there are others that I'm forgetting right now. And they're open source gems. And I'm not here to sell you any paid services, so I am going to talk about the open source gems. And actually, some of the paid services like CodeClimate use some of the gems, so it actually helps you understand how they work. Now, these gems do a bunch of things, but 3 main categories, okay? Static code analysis is basically a tool that will read every single statement in your application and assign a complexity score for each statement, and so your entire code base. Oops. Then code coverage. There are tools that will basically track every single statement that gets exercised by your test suite, and they will tell you 80% of your code base is exercised by your tests. And finally, code smells. There are tools that will compare your code base to a database of known code smell patterns. And they will tell you you have 27,000 smells in your application. And that will give you an idea of what software quality is for this project. But yeah, like I talk about quality and I talk about maintainability in this talk. And what is software quality anyway? Well, there are hundreds of definitions out there, and bear with me, I'm not gonna go through all of them. I included only one rant in this talk, so it's this very short rant, but just because there are hundreds of definitions out there, it doesn't mean you can throw your arms up in the air and say, this is too complicated, quality is subjective, we're not gonna talk about it. I don't advise you do that because we're software engineers and we can definitely find a definition of software quality that works for our team. So that's what I recommend. You get together with your team and you say, okay, we're going to use these tools and we're going to use these tools in this particular way to show that our code has quality. Okay, rant over. So let's go over a few definitions so I can talk about a particular section of code quality. So the IEEE, of course, got together and said, okay, it's the degree to which a system, component, or process meets implicit and explicit requirements. And of course, yes, this definition was defined by a committee that, yeah, definitely came up with a great definition. But to me, in my day-to-day, it looks like this. It works as expected. But actually, it's not just that. It works as expected is not enough because it could work as expected, but if I look at the code, it could be a mess. So to me, it works as expected and it is not a pain to maintain it. So that's what software quality is to me when I look at a project. Then if we look at the ISO 9126-1 model, we'll see that software quality has 5 different aspects. And I'm only going to talk about one of these aspects, which is the one I care about, which is maintainability. And to me, maintainability has 2 components. And the first one, the order is actually important when I talk about this. The first one is code coverage. Code coverage tells me whether an application has tests or no tests. And if it has tests, how extensive are they? I know that this metric doesn't tell me whether the tests are good or bad. I will need to review the tests and check that they're actually testing behavior. But this is crucial because when I inherit a project, I want to make sure that there are tests that verify the behavior of the application. And it will affect the next factor, which is code quality. Before I go in and I start refactoring a module or a file that is super complex, I want to make sure that there are some tests that are covering the basics. So I'm not going to go and modify a file that has no coverage because I don't like working weekends and I don't like putting out fires in production. I like to work with code that is somewhat tested. And I want to get feedback right away that my changes are not only making the code better, but also maintaining the same behavior. The good news is that in Ruby, we have tools that help us a lot with these things. So for code coverage, we have SimpleCov, which is a really cool tool that's been around for a while. And you can install it in your gem file like this, and then load it in your spec helper if you're using RSpec. Now, you don't want to load it every time, so that's why there is an environment variable there. And what this does is it configures SimpleCov to track a bunch of files that and to see how many of them get exercised, how many statements in the files are exercised. And you run it like this, and it will generate an HTML report that tells you that this project is in pretty good shape. There are tests that cover about 80% of your code base. Cool. Now, by itself, it's not enough to say, okay, this is a quality project, this is quality code. So then we need to assess code quality. And for that, in Ruby, we have dozens of projects. There's Flog and Flay and Reek and Ruby Critic and Metric Foo and all that. The one that I picked for this talk is called Ruby Critic. And I like it a lot because it uses some of the other tools. It uses Reek, it uses Churn, it uses Flog, and it helps you understand how many files are messy and how many are okay. And Ruby Critic uses two concepts that are very important, I think, churn and complexity. Now, Sandy Metz and Michael Feathers have written really good articles about churn versus complexity, which is a graph that can help you understand where the complexity is in your application. Now, churn is the amount of times that a file has changed since the beginning of the project. The good news is that for that, we have software code management systems like Git or whatever, Mercurial, whatever. Churn is basically the amount of times that a file has changed. So you can do git log default RB, and this will tell you that default RB has changed 3 times. And that means that the churn count for that file is 3. Now, by itself, this metric is, interesting, but not super useful. It will tell you which files have changed the most since the beginning of the project. It starts to become super interesting when you combine it with complexity. Now, for complexity, Ruby Critic uses Flog and Reek. Flog is this really cool tool by Ryan Davis from Seattle.rb. And you can pass a file name and say Flog default RB, and it will tell you this complexity score for this file is 10.8. And what does that mean? Like, I have no idea. Well, if you look at the way it works, it assigns a score to every single operation and every single statement. So an assignment is 1.2, an eval is 6.0, and so on and so forth. And the sum of all those scores is the total complexity of the file. And cool, okay. By itself, it also tells you, okay, this file is not that complex, but you can't really gather insights from this. When you combine the two metrics, it's really cool because you can start to gather insights about the technical debt in the project. The graph looks like this. In the y-axis, you have complexity, and the x-axis, you have churn. So if a file has changed 2 times, but complexity is 100,000 Flog points, you'll have it in the upper left quadrant. And if it's changed 27 times, but complexity is 100, you'll have it in the lower right quadrant. Now, to run Ruby Critic is super simple. You do gem install, and you run it like this. And this will run a bunch of tools that will statically analyze your code base. And it will generate a report that looks like this. Now you look at this, and the first time I saw it, I was like, what does it mean? Like, is this project great? Is it a mess? Is it the tar pit? Like, I have no idea. Okay, so let's look at it side by side. The GPA pie graph is basically a score of every single module, every single file in your application gets a score. The GPA goes from A to F, so A being the best, F being the worst. And the cost of the modules is calculated by a sum of complexity and code smells present in that file. So, okay, when I look at this, it's like, okay, 25% of the files are pretty bad shape. They're a D or an F, but okay, 75% of the rest of the project is okay. I can't really gather insights. It doesn't really help me figure out what I need to do next. Now this graph does, in a way. I see all these files, and I know that every single file in my project is in this graph. And to understand what it means, it's really useful to draw a line like this to split the graph in 4 different quadrants, like this. And there's actually only one of them that is super interesting, and we can actually start paying off technical debt if we focus on that one quadrant. And it's not this one. This one is the good place. Like, you want files to be simple. You want files that don't change a lot. If they're not changing, they are not costing you time and money.
Ernesto.
Sorry, yeah.
No, I apologize, given this is new to us. Can you send over the host privileges back to me? I just want to see if anybody's in the waiting room. I apologize. This is something we didn't totally think through.
Oh, okay, yeah.
The way we have it right now is one host has to actually see if somebody's waiting. So we want to.
Oh, got it. Okay. How do I get back control?
Okay, so hold on. Andrew made me co-host, so I think you are good to go now, and I'm going to get those notifications if anybody comes in. I apologize.
Oh, okay, cool. No worries. We don't
Okay.
want people just waiting there.
Yep.
Cool. Okay, so yeah, going back to the quadrants. Oops. Yeah, this is the good place. You want your files to live there. If that usually means that they're in really good shape. Now, the files that you find in the high complexity, low churn quadrant, it's like, okay, nobody understands those files, but they probably work because nobody's changing them. So I like what Sandy Metz says about these files. It's like, okay, if the code never changes, it's not costing us money. So if you're about to like pay off technical debt, these files are not your priority. Now, if you look at the lower right quadrant, you'll see that these are files that are super simple, but they change a lot. And they usually change a lot because they're configuration files or there are translation files or whatever. Like, usually it's not that important because you can open them pretty quickly and understand what they do. Now, this is the quadrant that has the most interesting files. These modules are complex and are constantly changing. And what Michael Feather says about these files is that sometimes a class becomes so complex that refactoring seems too difficult. And these files, you might know which files there are in your project because of the business type that your product is solving. You might have tried in the past to fix them, to make them better, but you probably run out of time, or you even made things worse. I don't know, but you want to refactor them, but they're not so easy to refactor. And when I look at this graph, I can quickly see whether I am getting myself in a tar pit, a dumpster fire, or maybe it's a good project. Sometimes there are some exceptions. And sometimes it will be simpler or easier to see than others. Like, if you look at this, I'll be like, okay, like every single file or like 80% of the files are complex and changing a lot. So this is a mess. Cool. So to sum up, we saw 2 different tools for these 2 different aspects about maintainability. For code coverage, we can say now we have one signal that analyzes every single module and tells us how well covered they are. And then we have complexity, which tells us how complex every single file in my application really is. But both of them are analyzing the same code base. So the question we had at fastruby.io was, what if we could calculate these 2 signals into a third one that tells us which files are changing a lot, super complex, and have no tests? And we decided to call that the skunk score. The skunk score is a function of code quality and code coverage. And the main idea behind this is that complex files which do not have any tests should be our top priority when we're about to pay off technical debt. And if we're about to upgrade Rails, which is what we do at Fast Ruby, we know that these files are probably going to have problems as we go along. So it's good to know that they're there. It might be easier to see this with an example. Let's say that we have user.rb, which has 10 points for complexity and for smell. So we multiply, 10 by 10, 10 times 10 is 100. And then we have shop.rb, same thing, same score. So if we look at them side by side, we might be tempted to say, yeah, user and shop are equally stinky. And no, like you can't really reach that conclusion because you're missing information. What if I told you that user has no tests? It's super complex and there are no tests. And what if shop has perfect test coverage? Every single public method is tested by a unit test or an integration test. Now, if you look at them side by side, we can see that they're clearly not the same. One has more technical debt than the other. And I say that shop is considerably better than user.rb and easier to maintain. And now we can actually make a decision about the time that we'll spend paying off technical debt. Maybe we want to commit to increasing code coverage to 40% for user.rb in the next sprint. So, of course, we are software engineers, and to be honest, we used to do this calculation manually. We would basically get the data from Ruby Critic and then from SimpleCov, and we would cross-reference complexity or complex files with least covered files, and then we would send the report in a code audit to our clients. And we would tell them these files are probably going to be a problem as we start upgrading your application. Well, the good thing is that, as I said, like 99% of the code was there. I had SimpleCov and I had Ruby Critic, which used a bunch of other tools to come up with all these data. So what we did is we wrote a skunk score calculator called Skunk. You can check it out. It's open source. It is still pre 1.0, so expect the formula to change in the near future. But this particular tool is an extension of Ruby Critic, and it combines Ruby Critic data with SimpleCov data. And you can install it like this and run it like this. Now, there is a caveat here. Skunk relies on you having coverage data in your coverage directory. So if you don't have that, that particular directory, you're probably not going to get useful information. So you need to run SimpleCov before you run Skunk. And this will generate a report that looks like this. So yeah, this is not HTML and it's still pretty ugly, but it tells you for every single file in your application, what is the skunk score. And at the end of the report, you'll see the skunk score total, which is not that important because, as you add complexity, that's only going to go up. What's interesting is the skunk score average, because it will divide the total by the total amount of modules, and the average will be important in the future. Now, to understand how it works, I need to explain how Ruby Critic calculates the cost of every module. It adds all the costs for the smells, which come from Reek, which will tell you all the smells that are in your module. And then it uses flog to calculate complexity, and then it adds everything together to calculate a total number. Skunk does something with cost. Basically, it adds a penalty factor so that if the module has perfect coverage, then the skunk score is going to be the same as the cost. But if the particular module has only 20% code coverage, you will have a penalty factor of 80 applied to the cost. And this will help you see which files are accumulating a lot of technical debt. So we now have a third signal, which is the skunk score, which is good. Now we can tell where we are in the map of like technical debt. And now that we know where we are, we can actually start taking decisions and making decisions to get out of it gradually. And that's where part 2 comes in. We use the tools from part 1 to guide us out of the tar pit. And how can we gradually pay off technical debt? Well, I think the 3 main ways to do this are these 3. Removing files or factoring them, or increasing code coverage. In order to remove files, there's this really cool tool called Coverband by Dan Mayer. And it's very similar to SimpleCov in a way, but the difference is that the source of truth is real production usage. So you can install this tool, run your application with it in production for a week, and then you can get a report that looks like this. And it will tell you which files are not exercised at 100%. You'll see that there's like an unreachable controller that it's only exercised 50% of the time. So maybe there is an action there that is unreachable and you can remove it. And that will certainly remove or improve the skunk score average. The next one is to refactor files. And we go back to the churn versus complexity graph. Now we see that there are 4 files there. And it's like, okay, cool. Which one do I want to prioritize? Well, I don't know. I don't want to just randomly pick one. So yeah, these are great candidates for refactoring, but I need more information. And I think that's when churn versus complexity is not enough. We need more information, and that's why I believe that code coverage can guide us in our next steps. So we go to the table and we look at all these files that have a pretty big skunk score. And we want to focus on the ones that have some code coverage, right? We don't want to start refactoring files that have 0% code coverage, because it would be a nightmare. We would have to manually test things, and we'd have to be like very sure that we're really good at manually testing things. But anyway, like let's pick the first one. Let's see that one. Okay, has 60% code coverage, which is not great, but it's better than nothing. What we can do here is say, okay, we're going to refactor these files. We find it in the graph, and here's where the manual work comes in. You will need to open the file and try to determine whether it can be refactored. For the sake of this argument, let's say that it has 2 responsibilities instead of 1. Let's say that it fetches and it calculates the churn count. Cool. Okay, that means that we can probably split that file into 2 new files. And you will see them move to the left, closer to the y-axis, because of course churn count will be 1 because they're new files. And hopefully complexity will diminish as you split the responsibilities into 2 different files. And that's good, because you refactor a file, you know that there were tests that tested 60% of the behavior. You might have to make some tweaks to the specs. But once you do, and once everything's green, you know that the logic is tested. It's not tested at 100%, but at least like 60% of it is tested. You might need to do some manual testing after that. And one thing that's really cool about Skunk is that you can actually compare branches. You can calculate the yeah, basically skunk minus b master compares your feature branch with master, and it will tell you that the average has gone down from 79 to 71, which is awesome. Like it's 10% better. You can even include this data in your pull request. Say, I didn't just pay off some technical debt. I paid off 10% off the technical debt are associated with the Git.rb. Cool. And the final one is increasing code coverage. Now, for that one, we also have to go back to the table and look at the files that are complex and have 0% code coverage. Now, I'm ignoring the first two with 0% code coverage because they're test files. I do care about the third one, which is a file inside the Ruby Critic project. It has a high skunk score. It's been recently renamed from stink score to skunk score, so that's why it still says stink score there. But anyway, what you can do is say, okay, what if I wrote like 50% or tested about 50% off this file? You could reduce the skunk score by half. So from 650, you could go to 325. Cool. Okay, so we talked about code coverage and complexity and smells. And these are factors that you can use to define your code quality standard on a project level or a team level. And I believe the skunk is a really cool tool because it provides us a way to communicate on a deeper level. So instead of saying things like, oh yeah, this pull request is paying off some tech debt, you could say, hey, this pull request has paid off 5% of our tech debt, which is, it's cool. Or next time you inherit a project, or next time someone tells you, hey, can you start maintaining this project? Instead of telling you, yeah, this project is in pretty good shape, they could tell you, yeah, this project has a skunk score average of 120. And what I love about this is that everything is open source. Like you can go to GitHub and you can look at the formula, and if you don't like it, you can fork it and create your own formula. The next step in skunk is basically to work around the weight that every single factor has in the formula. That's still needs some love. But another thing that I really like about skunk is that it's easy to configure. You can basically set up Reek to ignore a bunch of things, and then the skunk score is going to change based on the standard of code quality that you have defined at a team level. So I really like that part as well. And I think this could be a really cool tool to guide you out of the tar pit. So when you look at the files that are in the upper right quadrant, you can decide what you want to do next. Do you want to write tests for these super complex files? Or do you want to refactor these files that have decent code coverage? Well, that will be up to you. You'll have more information to make a decision. And if you start tracking the skunk score average over time, you should see it go down if you're dead set on paying off technical debt. Another thing you can do is look at the skunk score average and see whether it's going up exponentially. That could be a problem. It could be a problem with your team or with the project. But something that you don't want to see is like that average go up exponentially. Cool. So yeah, thanks a lot for being here. Hope everybody's doing well at home during this crisis. If you're interested in this topic, feel free to check out the project on GitHub. If you need help with your Rails Operate projects, feel free to check out fastruby.io. We have a bunch of articles about our process, and you might find it interesting. And if you have any questions and we don't get to them today, you can reach out to me via Twitter, and I'd be happy to answer them. I will be uploading the slides after this to the Meetup page, and you can find them over there. There are a bunch of resources. Oh, one thing I forgot. If you submit an issue or a pull request to Skunk with an improvement or an idea, I'm happy to send over a sticker.
Lovely.
Yeah. And thank you.